Okay, it's being recorded.
Perfect. Thank you.
So as I was saying before I was reminded that I should be recording this, it's a real pleasure today to introduce Dr. Jin. And Dr. Jin is an associate professor of geophysics, and he's the co-director of the Reservoir Characterization Project at the Colorado School of Mines. And his interests are in distributed fiber optic sensing, and their applications in geophysics, as well as seismic imaging and machine learning applications. So he initiated and developed several important distributed fiber optic sensing applications for oil and gas applications. And I think many of us have read some of his seminal papers on this topic. And this includes cross-well strain monitoring, DAS-based microseismic imaging, DFOS-based production logging, and reservoir characterization. And before joining Mines, Ge worked as a research geophysicist at ConocoPhillips for 5 years. And he obtained his PhD in geophysics from Columbia in New York City. And he has a dual BS in geophysics and computer science from Peking University. So a real pleasure today to introduce Dr. Ge Jin.
All right. Thank you very much for the introduction. And it's really a pleasure and a greatly honor to be invited to give this talk. This is something that, we work with AETL as well as with my consortium, and we explore the data, we explore the theory, and we find something really, really interesting, some relation that we have been ignored for a very long time. So I would like to just have a fun discussion with this crowd and also share with, what we find through this work. First of all, I would like to acknowledge my co-authors, my student Pei Li, and he's definitely the main worker of this research project, and also our collaborator Rick and Colton from NETL, and also NETL is partially funding this project, and also Dr. Kang Wu from Texas A&M, who provided some theoretical support for this work. Because it's partially funded by NETL, I'm required to put this disclaimer here. Basically, it says that DOE funded this project, but the US government doesn't have to agree with me. Although I do hope they agree. So yeah, so that's it. If you have a very short time and this one will be recorded. So if you only have 3 minutes to listen to this talk, and here's the key takeaway. So we found there's a very linear relationship between the hardship signal that measured by the crosswell strain measurement and the fracture tip distance to the monitor well. If you don't know what I'm talking about, that's fine. I will give you an introduction on both of these concepts. And the usage of this funding is it can constrain fracture propagation in the far field from the monitor well, which is, we believe, is pretty important for understand the hydraulic fracturing process. And also have a couple very important practical applications. So the outline of this talk is first I will give a introduction on both fiber optic sensing and also what do I even mean by hardship signal, right? So if you're not familiar with the fiber measurement, that could be not very straightforward. I will give you an introduction on that. And then we were talking about what does this hardship signal, what determines the shape of these hardship signals, right? And what impact that. Then we discuss that this very interesting relation we find, we show that, apply that on the field data before I conclude the talk, and also have some further discussions, hopefully. So distributed fiber optic sensing is really a relatively new technology that being applied in both in the field of the geophysics and applied engineer and the petroleum engineering. Although the technology itself had been developed by 30, 40 years ago, but the precision has been of the measurement has been increased pretty significantly in the last decade. So that started promoting borehole usage of the technology. The technology itself, just from the theory behind it is pretty complex, but just from a user point of view, if you're just using it but not designing the instrument, It's pretty straightforward. So if you have a fiber, this is actually the same fiber we use for internet, right? So if you use choose the your internet service, a lot of time you'll find there's an option that for fiber internet. Usually that's much faster than the traditional standard. So this is the same fiber we use for internet transported data, but if we connect one end of this fiber with an instrument called interrogator, and this interrogator will keep sending laser pulses into the fiber and measure the backscatter energy or the energy that's reflected along the fiber. It can measure the temperature, vibration, and the strain everywhere along the fiber continuously in both space and time. So this is a measurement that is very different from our previous measurement, like a point sensor measurement that you only measure a location of that physical property you're measuring over time. But this one is continuous in both time and space. So the data we receive is naturally two-dimensional. So one dimensional is time, one dimensional is space, and the space is along the fiber distance. So for this particular talk, even though we can measure multiple things, but for this particular talk, we are focusing on distributed string sensing. So what is really measured is the very tiny extension or compression of the fiber anywhere along this, fiber pathway, right? So it's basically you can consider if I believe a lot of people joining this meetings are familiar with the geomechanics. So if you're familiar with that, so what we're really measuring is the string, single component string distribution along this fiber, and that's the that's a projection of the string tensor along the fiber direction. Oh, I just noticed the first author of the work, Peiyao Li, just joined this. Hi, Peiyao, and thanks for joining us. And tell me if I made anything wrong. So let's continue. So we're talking about the distributed string sensing. So the instrument nowadays, the modern instrument can measure up to 8 kilometers of fiber of the entire fiber length, and with a spatial resolution of 0.2 meters. That means that, remember, we're recording a two-dimensional data. Along the spatial direction, every 0.2 meters, we're able to measure a string value along the fiber. And the sampling interval changes depending on the technique you're using, can be either from 0.1 seconds all the way to a couple of minutes. But we're talking about like relatively low frequency changes of string. More importantly, and how that different from that's why this technology is being applied so much recently is the sensitivity improvement. Nowadays, the modern DSS measurement the sensitivity can reach to 0.1 microstring or even lower. So some instrument claim they can measure like a couple tens of picostrings. So this is pretty significant, and we're talking about 10 to the minus 7 to 10 to the minus 8 of deformation that is very comparable to the deformation that induced by the propagation of hydraulic fracturing. So that's why we're making so many different new observations that help us to understand the hydraulic fracture propagation. So if we place this fiber in the borehole along a horizontal well or a vertical well, we're able to capture the string perturbation induced by the hydraulic fracture propagation. So here shows really a simple simulation that we have a treatment well or injector that create a hydraulic fractures. And then in the nearby, we have a monitor well. In this case, it's likely to be a horizontal monitor well, and instrumented with a fiber measurement, and we're using distributed string sensing or DSS continuously measuring this monitor well. And what is being plotted along this monitor well is the string component that is parallel to the well path that induced by this propagating hydraulic fractures. So in here, you can see that on the right is showing what the data looks like. Again, as I said, DSS measure a two-dimensional data. So vertical is, distance along the well, and horizontal is time. So this plot in here is called the waterfall plot. So color means the string measurement, and red means this portion of fiber being extended, and blue means this portion of fiber is being compressed. So, if you're familiar with the geomechanical modeling, a lot of you can start recognizing this classical response on the data, and you see this compressional signal on both sides of the fracture. Those are usually called stress shadow. And also right before the fracture hit, let's pay attention to here. Right before the fracture hit, we see this extensional signal this is what we call the heart shape. It's similar because you can see it looks like a heart, right? So these are extensional processing zone in front of the fracture tip, and it's actually helped the tensile fracture to propagate. So these are just simulation, but more importantly is we are able to measure very similar results in the field. So on the right is actually a field measurement, and with a single fracture that intersecting the monitor well. And on the left is a history matching of what that geomechanical model predicts. So you'll find that these two really ensemble with each other. We find this very nice heart-shaped signal that before the fracture hit, right? So this location we can recognize as a fracture hit. This is the intersect the time and the location of the hydraulic fracture at the monitor well. And before that, you see this really nice heart-shaped signal. And also after fracture hit, you observe this stress shadow on both sides of the fracture. And keep in mind for people not familiar with this topic, so what we're measuring here is the strain rate, is the change of strain. So that's why you don't really see the stress shadow are increasing with time because this is a strain rate. It has the maximum when it's the fracture hit, right? So this is very nice, and currently the most usage of this signal allow the industry is really just picking the time and the location of this fracture hit, and also afterwards we use geomechanical model to invert for fracture aperture. So basically for characterize individual hydraulic fractures. But one thing has been missing in the analysis is, what does this hardship signal do, right? So because right now most of the analysis is just happening after this, but this hardship signal also can be useful, and also it's actually represent the fracture propagation or help us to understand the fracture propagation between the treatment well and the monitor well, instead of just only characterize after it intersect with the monitor well. So that's basically the goal of this particular study is how we use this particular signal. Before I step into our theory, I have to acknowledge that we're not really the first group that studied this. Our colleague Smith Kellett from Texas Tech University has been working on this for a couple of years. And his technique is actually focusing on the zero crossing of this heart shape, that the transition location between the extension and the compression on here. And he find that the distance of this two zero crossing on the heart shape signal is related to the tip distance of the fracture to the monitor well. However, he find that this distance is very complex. It's determined by the shape of the signal, the shape of the fracture, and also the relative well distance, well location compared to the fracture. So it's a great finding, and that means that the hardship is related. The geometry of the hardship is related to the fracture tip distance to the monitor well at a certain time. But the relation is so complex that you have to make a lot of assumptions even before I use it. So when I look at this, as a geophysicist, I have two issues, not really issues, or thinkings of that. So one is the zero crossing in the real data is usually represent the lowest signal ratio because your signal there is a zero, right? So you don't really want to pick that, in the data because it's subjected to the noise pretty significantly. So instead, can we use the maximum amplitude location? Because that represents the highest signal to noise ratio location or regions in the data. And also the relationship is very complex and fracture dependent. Is there a simple relationship we can find or we can identify in the data? To answer these two questions, and we are using a classical DDM model that are able, so even though it's based on a homogeneous material response, but we're looking at the near field, so hopefully we're not too off from the field data, real case, but also allowed us to simulate a lot of fractures in a very fast way. And so in this case, we're testing all these variables, the fracture height, fracture width, and also the monitor well locations, and also the horizontal location and vertical location. We're testing all these variables to see what control the shape of that heart shape and what we can use that. We can, is there any sensitivity and how we can use the heart shape to constrain the fractures. And also we tested a classical elliptical fracture and which the fracture height and the fracture width both are changing with along the fracture length direction. We also try the right angular or cubic fracture, which the fracture height and the fracture width does not change with the along the fracture length direction. So we tried these two extreme cases to see, does that even have an impact on the heart shape signal? And also the signal we use, instead of looking at the zero crossing, the signal we use is actually looking at the maximum, the local maximum of this heart shape signal at each time step. So again, this is what we usually measure on the data. And the processing flow is very simple. So for a one particular time, and you just extract the string profile or string rate profile at this particular time. So we're just grabbing this column of this matrix and find the local maximum, and we measure the distance of these two local maximum. So this algorithm can be very simple automated, and you don't have to handpick this. And also, it's the maximum; it's much easier to pick. So we start with a synthetic. In this particular case, we start with a base case that our monitor well and the center of the fracture are, or the injector location are about 200 meters away. And also the monitor well have the same depth of the treatment well. We say the maximum fracture height is 60 meters and the maximum fracture width is 1 meters when it's reaching the monitor well. So it's an elliptical fracture. And on this plot, you're going to see this plot a lot. In this plot, what we're plotting is on each time step, you can imagine as the fracture growing closer and closer to the monitor well. So for each time step in here, we're estimating the fracture, the peak distance of these two peaks on the heart shapes, which we call the D peak, distance of the peaks. We plot it as the horizontal axis. And the vertical axis is at the same time step, because this simulation will know where the fractures are. We measure the distance of the fracture tip to the monitor well. So this is being plotted on the vertical axis, which is the D frag. So distance to the fracture. And because we have the fracture are growing, so we have many dots in here. So because in the beginning, the fracture tip are pretty far away. So as the fracture grow, we actually from the far end of this plot and then growing into this as the fracture grow closer and closer. And here is where the fracture intersect with the monitor well. So on this plot, immediately you see this is on the base case that this is a very interesting phenomenon that you find in the beginning, this heart shape signal, this relation is quite nonlinear, right? So, but once it gets to a certain distance, then this two relation becomes just a linear relation. And so the distance to the fracture is a linear scale of the distance of these two peaks. So this is really cool because a linear equation is, people love linear equation, right? So because you can almost calculate it just by a simple calculator. And but the question here is, how linear is this, right? So what control this linear relationship? And also, what control this distance at the start is start to get into this linear regime. So that's the question we're trying to answer through more modeling. So the first thing we are changing, in the beginning, we're changing variables one by one. So let's try if I change different fracture height and also try different fracture shape, right? So it's an elliptical fracture or right angular fracture. I see, does that change this linear relationship? And we find that by changing different fracture height, we're changing fracture height all the way from 30 meters to 60 meters, which are base case, and to 90 meters. We're changing almost like 50 to 100% of variations. And we find that in the elliptical fracture, amazingly, in this particular case, it doesn't even change this relationship at all. So see, this is not an error. This is actually all these three color plots just call plot on top of each other. So that's why you only see one single fracture color in here. So fracture height doesn't impact this relation. And for right angular fracture, you see it's impacting just by a little bit. We're just having like 5% of variation on this, but it's still maintaining almost the same linear relationship. So that's interesting, right? That's very interesting. So the height doesn't change. How about the width? The width doesn't change either, right? Because if you're familiar with the DDM, this is actually building their assumption because the width is just a linear summation of it's just impact the amplitude of the string field, but not the shape of the string field. So this is kind of expected. Changing the width of the fracture doesn't change this relation at all. How about the next one? How about we're moving the monitor well up and down, right? So in the vertical domain, because in the real hydraulic fracture cases, the monitor well and the injector may not be in the same formation, right? They may have some vertical offset. By changing different vertical offset, we also find that we change it all the way, from 0 meters to 120 meters. Remember, in this particular case, the fracture height is only 60 meters. So we're actually moving the monitor well much higher than the fracture height can reach. But even in that case, we find that it doesn't break this linear relationship. This linear relationship still exists pretty pronouncedly with all different type of the fracture vertical locations. Same thing for the right angular. Again, there are some more scatters for right angular case, but in general, the same linear relationship still stands. So this is pretty cool. And at this point, we're changing all the possible variables, except for one, which is the horizontal offset. I will talk about it later. But we're changing this vertical, we're changing this, height and the width, and the fracture length is always changing, right? So because we're propagating a fracture like that. And all this all lie into the same linear relation. So what that relation is, right? So we'll conduct the linear fit of this. We find for elliptical case, the peak distance on the sharp hardship, the distance you read on the hardship is about 80%, times 0.82. That's a magic number. And you got the distance to the fracture tip. So that's really cool. And also this relation doesn't really impact on the height of the fracture, width of the fracture, or the vertical well or the monitor well locations. For triangular fracture, that relation is slightly different. So it's a 0.9 instead of 0.8, but still the linearity is very, very strong. But also we find that there's a magic number in this case, which is this linear relationship only happens if the tip distance is less than 150 meters. So does this one changes? So then the last thing we change is we are varying the horizontal well, the monitor well distance horizontally. So we're moving it closer to the treatment well or moving further away for the treatment well. And we're also combining all the possible variables, fracture height, fracture vertical distance, and everything on that. We find the same relationship still stand. It's still 0.8 times peaks for elliptical. And but where that this linear relationship breaks, it dependent on the horizontal mount well distance. So this is very interesting, and also this is really cool, right? So this is a very simple relation. We can predict how far away of the fracture to my monitor well at any time, as long as I can see this hardship signal in my data. So for the right angular fracture, as I mentioned, is a slightly different coefficient, is 0.9. But considering in the field data, in the real case, that the fracture is likely to be more similar to elliptical fracture than right angular fracture, because we do believe the fracture height and fracture width should be changing along the fracture length direction, and we do have field data of supporting that. So we're basically using this relationship 0.82 for the prediction, right? So once you know the relation, you start to making the prediction. So this is the prediction result. And it's really just a linear scale of the plot that I previously had. And you find that the horizontal is a true fracture distance and the vertical is the estimated fracture distance. You find that for elliptical fracture, we're able to predict the relation really nicely until you'll find the fracture is too far away from the monitor well. But that threshold is actually changing with the distance between the injector and the monitor. I'll explain why. And if we use the same relation to predict the right angular fracture, I think the prediction is still pretty good. We're about 10% of bias because they are following different correlation, different coefficient. But considering the right angular fracture is not unlikely to happen in the field, we treat this as the maximum error of our prediction, right? So this is actually nicely even even your fracture is way off than the elliptical fracture. I think the prediction is still accurate within about 10%. But we didn't stop there because we kind of confused in a way that, it seems to be a nice relation we find. It doesn't really matter, depends on the Monte-Carlo location and the fracture geometry, but that linear relation does break at a certain point. So what's causing that? And also, is there any fundamental, what are the fundamental physics that connecting this heart-shaped signal with the fracture tip distance? And what are the assumptions and the limitations of this prediction? This is something that DDM will be very difficult to derive from the DDM, because DDM is it's an analytical solution, but it's also a semi-numerical solution, right? So we have to break we have to break the fracture into many pieces to make the summation of that. So it's a little bit difficult to derive directly from DDM. So this is inspired by Ken, and so Ken actually doing a communication. I'm showing this with Dr. Kamu from Texas A&M, and she said, "How about let's go back to this century-old theory about the fracture tip string distribution around the fracture tip, and let's see if we can find the same relation, in that century-old signal. Maybe it's there, right? So maybe we just didn't find it." So we look at this century-old signal. You see it was published almost 100 years ago. And this solution here, which gave you the string stress distribution around a fracture tip. And this formula here, if you read the textbook, you'll find this is actually a classical, the assumption to derive this equation is this has to be a 2D fracture, and also is a near tip solution. Means that the solution, the space here, near to be very close to the tip. If I change another word on this, is that means that compared to the solution you can get is compared to the distance of what your monitoring point to the tip, the fracture length and also the fracture height, which is inside outside of this of the screen, both of these two dimensions has to be infinitely large. If you assume that, you will get this solution here. And we can easily change this solution into a string distribution on the YY direction in this case, and which are presented here, right? So one little trick I have to play to convert this measurement, because this is really how the spatial distribution of the string away from the fracture tip. But what the fiber measure is the string rate at a fixed location as the fracture propagates. So the only trick I need to play is, the string rate is the temporal derivative of the string field and of the string measurement, which can be, related to the spatial gradient of the string field versus the dx dt. And dx dt immediately is a velocity. So what I did here is really just changing, instead of fracture propagating towards the mountain well, I keep the fracture fixed and I move the mountain well towards the fracture tip. So this is equivalent, is really, anybody know the physics, learn the physics, you'll know this is just changing your coordinate system, but the physics doesn't change. So that means that we can simulate using this equation, we can simulate a string rate measurement just by taking the spatial gradient of this signal. And this is exactly what we did. We take the spatial gradient of this analytical solution. We find we observe the same heart-shaped signal. And we measure the local maximum at each fracture at each time, right? And we measure the distance. And also, this analytical solution, we know what's the tip of the fracture distance is. And we create the same plot, and d peak versus d tip. And we find there's a linear relation, and that linear relation is 0.801. It's just a very little difference than our measurement, our DDM solution of 0.82. So this relation, we didn't find this relation. This relation is already there in a century-old equation and theory that tells you the spatial span of the heart-shaped signal is related to the distance of the fracture tip to your monitoring point. That's awesome. But the more importantly is this analytical solution really can help us to understand what's the limitation and assumption that we're making to be able to make this relation work. So again, this relation is hidden there, and we just rediscovered it and applied it to modern measurement. So what are the insights we can get from this analytical solution? The first one is the analytical solution, you can only derive that equation based on the assumption that this is a near tip solution, means that the fracture height and the fracture length need to be infinite, right? So you find then that's actually a relation that we can get inside immediately, means that whenever this thing break, it must be because we're breaking this assumption. And it means that the tip distance should be start to get not small enough compared to either fracture half-length or the fracture height. So in this case, if we're focusing on the fracture half-length, then we find actually this basically we can quantify this assumption or the criteria with a tip distance divided by the fracture half-length. And this ratio needs to be small enough to make this relationship linear. So however, in the real field example, we cannot get the fracture half-length all the time, right? But in the field data, it's more convenient to use the well distance because I know where my injector is, I know where my monitor well is. I can calculate the well distance very easily. And then we can basically, based on this very simple geometry, we'll see the ratio between the tip distance to fracture length distance is equivalent to be the tip distance divided by the well's distance, which we already know. And these two are linear correlated with each other. So this tip is need to be small, means that this one need to be small. So, but the contribution here from the DDM is we can determine how small is small, right? So what we find is actually it's not that small. As long as, and here is actually the changing the co-plot of the prediction error of all the models we test with a different treatment well and monitor well distance. What we find is that as long as your estimated fracture tip distance divided by the well spacing is less than 60%, then this linear relationship is valid, and you can use it to estimate the fracture tip distance. This is pretty good. For example, if we have a injector and mounted well off by 200 meters, that means that we can measure the fracture propagation for over 120 meters over this distance. So that gave us a lot of insight into this. So that's the number one insight. And actually, what controlling whether it's a linear relation or not is really just this ratio. Is the tip distance divided by the well distance. As long as this ratio is less than 60%, then you can make reliable measurement or estimation of the fracture tip distance. And the other is it also helps us to explain that why the right angular fracture have a slightly different linear correlation than the elliptical fracture. So if you look at the analytical solution, the assumption is we have an infinite fracture height, and also is elliptical fracture. The width increase with the tip elliptically. So we got a relation about 0.8. That's the coefficient. So for DDM elliptical fracture, the fracture height and the width increase elliptically. Both height and width increase elliptically from the tip. And we got a very similar coefficient. It's just slightly increased from 0.8 to 0.82. For right angular fracture, we have a constant height and width. And that's actually gave us the 0.9, right? So you can imagine that from the height side, the right angular fracture is the same as the analytical fracture, and the width is different. But elliptical one, the width is the same as the analytical fracture, but height is different. So because these two are very similar to each other, so you'll see actually this coefficient is mainly caused by the width versus distance, by the width changed spatially, but not by the height changed spatially. So the fracture height doesn't seem to have a big impact on this coefficient. It's just the width, the shape of the fracture tip are controlling it. Again, back to the field example, because we're likely to think that in the field, the width are likely to be increasing, from the fracture tip towards the treatment well. So we think we can safely use this 0.8 or 0.82 coefficient to make the field example, to field prediction. So all this analytical derived, and all you need to remember is just two coefficient. And that's why I really like this work, because it makes our life much, very, very simple in the field. One is you can make this prediction, only when your estimated fracture tip distance is less than 60% of your well spacing between the treatment well and the monitor well, right? So that's the number one. So let's say if I have a well distance, this is the actual field example. The well distance between the treatment well and the monitor well is 205 meters. That means that I have this times 0.6. That means that I can safely predict the fracture tip distance as long as the fracture tip distance is less than 130 meters. So that's the number one. Number two is in your field data. So this is field data. You can easily pick the local maximum of this hardship signal and the distance of this local hardship times 0.82. So it's just as easy as that, times 0.82. And you can get this fracture tip distance at this particular time to your monitor well. So if you apply this to every single time step of the data, you can nicely see a propagation. You can track the propagation of your hydraulic fractures with a very high temporal and spatial resolution as it propagates towards your monitor well, just like this, right? And then you can measure the speed of that propagation very nicely just by fitting a linear line of this. And also it's quite interesting to see because, once we start measuring when the fracture tip is less than 130 meters away, you find the fracture actually propagates with a very constant speed. It's at about 0.5 meter per minute for this particular example. This is a fracture that in the monitor well, in the Permian Basin. So, but also you find that there's a little time that, but for the first 80 meters, because we can try 130 meters, but for the first 70 meters, we know how long it takes for the fracture to grow to that point. We find for the first 7 minutes, the fracture propagated much faster at the 12 meter per second, and then it slows down to about 0.5 meter per second and constantly propagates. So I won't go into too much detail. We're still testing all the other stages to see how consistent this observation is, but it definitely tells a lot about how hydraulic fracture grow in your reservoir. And you really are tracking, minute by minute on how the fracture grows in this particular case. So this is a really cool observation and very powerful tool we can use. So potential applications, this is such simple case and you can easily apply in real time in the field data. Even if you're a field engineer, you can observe this in real time. Though most of the vendor nowadays can produce real time low frequency data in the field. So you can really just start counting like your fracture is 50 meters away, is 20 meters away, is 10 meters away. So just by that is that really help us, to understand a lot. We can, by estimating the fracture propagation, we can optimize our completion design because by the end of the day, we want to get a more even fracture distribution in our reservoir. And also, if you're in a case that you don't want to see a fracture hit, for example, in the parent well case, you don't want to see the fracture hit at the parent well, and you are able to use this signal in real time to prevent the fracture hit because you can tracking, oh, my fracture is 100 meters away, now it's 50 meters away, now it's 30 meters away, let's stop pumping and let's stop the fracture propagation at this time. And also, more importantly, more interestingly, is it gave us a mean to constrain the hydraulic fractures in the far field, right? So even though this relation have a lot of constraints, but we can derive very simple, easy relation based on other geometry of the data. I think it's more importantly is we can more constrain far field for fracture propagation based on the string data, and so also use this relationship to predict what the fracture looks like. So this is still a ongoing work, continue to be funded by NETL. We're actually developing inversion algorithm based on string data for the fracture deformation in the far field. So here's the conclusion, and we identified this a really, really interesting linear relationship between the hardship signal we observe in the field and the fracture tip distance. We find this relationship is hidden in the century-old analytical solution, and we investigate what's the assumptions of that and what's the limitation of that linear relationship. What's the criteria that you can be applied on this linear relationship based on a more modern and complete DDM modeling. And this linear relationship is very easy. You can already memorize that. It's a 0.82 times your hardship distance. Can really help us to constrain the fracture propagation in the far field from the monitor well, which may lead to many, many potential applications, as I mentioned before. So at point, I think the time is pretty good. And I would like to thank NETL and also my consortium, Reservoir Characterization, all the sponsors listed here for the financial support of this project. And now I'm open for questions. Thank you very much.
Well, thank you, Ge. And indeed, you do have a lot of questions. It a fascinating presentation. And
Thank you.
so I don't know whether you can see the questions or whether you'd like me to read them.
Oh, yeah, I turned them down and there's wow, there's a lot of questions. Okay, so let me see here.
Maybe I'll paraphrase them and
Okay, yeah, that'll be great.
so the first question is from Alexei Savitsky, and he really enjoyed this. Excellent piece of work. He would like a fundamental definition of D peak.
Okay. Sure. So I think it's also, is that more like how uniquely you can estimate from the field data. So this is really the field data. And we do a little bit processing to, beat down the noise level. But what the D peak is, so this is the hardship signal. So let me go back all the way to, what its original looks like, maybe give us a better idea. So this is the original data looks like. For each time step, you see this is a 2D matrix. For each time step, you can extract the trace out. And this trace, let me see, I can probably do this. This trace will probably looks like this, right? And then we'll go another peak in here. And then, so this is basically just at this time step. You track the trace, you plot it against the measure depth, and this is a string profile you'll get. And then you can just, estimate these two local maximum, the location of these two local maximum, and then you measure the distance of these two local maximum. That's the definition of the D peak in the field data. And we find actually by applying some smoothing curve is actually quite uniquely determined, can be quite uniquely determined in the field data, just as you see, we show in this field data example. So these black dots are the automated picking result, just writing a very simple Python algorithm. And you find that interestingly for each time step, it always pick two peaks when your signal level is high enough.
Excellent. And Mirko van der Baan, Mirko argues that the heart-shaped tip is related to the shear lobes. And maybe you've accounted for this with your mode 1 simulations. Not the tensile deformation zone. So would the size of the heart not be related to the rock's compliance and indeed to the shear moduli?
So I don't think, because what we're measuring is string, and so you can see in this, let's go back to this, heart shape thing in here. So this is the analytical solution where this 0.8 comes from. And I believe in the K here, the only thing that going from the rock property, the only thing going to this is the Poisson ratio, which are showing in here. So we did test the different Poisson ratio. We found it doesn't really have a big impact of the coefficient, but it's really not the Poisson ratio and the Young's modulus in here. But Young's modulus, you can see, is just a scalar. It's determine the magnitude of the string, but doesn't the shape. So the Poisson ratio have a little bit impact on the shape, but the impact is quite minimum.
And Yongjan has two questions.
Mhm.
I'll ask you the first one while I read the second one. So do you assume, and I think you've covered this, but maybe you can reiterate, do you assume a constant fracture width? And he's arguing that there's a strong width gradient near the tip.
There, for elliptical case, there's a strong width gradient from the tip. So this is actually, you can consider this as height or the width is actually the same. So for elliptical, the tip shape like this, and for right angular, there's no gradient of the width towards the tip. So you'll find actually the analytical solution, because it's based on the elliptical fracture, it's the 0.8 is come with the assumption that you do have a width gradient towards the tip.
And his second question is he argues that fractures propagate sporadically, and have you run any cases where you've stopped fracture propagation temporarily and then restarted?
I don't think that will change the result, because this is really a kinematic solution. So it's just based on the fracture just based on the fracture. Oh, sorry for that. Just based on the fracture geometry. The only thing, again, I think this analytical solution is so helpful because it's help us to understand the physics very well. Let's go back in here. So if your velocity, let's say your velocity increase, decrease, or changing, based on this equation, what you'll find that unless it's changing very, rapidly, but if it's a smooth changing, you can assume that this is only changing the magnitude. Again, it's only changing the magnitude of your strain rate, but not the shape. The shape of the strain rate, where that the two peaks located, is just dependent on the spatial gradient of this analytical solution, and the velocity of the fracture is just a linear scalar to that to that shape. I hope that answered your question, Yunzan.
Ed Siebritz, Ed appreciates this, and he's interested. What would happen if the rock was not linearly elastic?
Oh, we're in this particular case, we're making the far field measurement. And so the deformation, the strain we're measuring, as you can see that the fiber can measure 10 to the minus 7 to 10 to the minus 8 strain deformation. So we believe especially on the hard shape side, we believe it's still in the linear stress regime. So we don't think, of course, when you get to the fracture hit location, so let's go back to the field data. When you go back to the fracture hit location, so there may be some, there definitely will be some non-linearity happening. But when we're far away, I don't think we need to worry too much about the non-linear deformation.
Cool. And your colleague Joseph Mihovich, Joseph wants to know, it's a similar question that was asked
Yeah.
before.
Mm-hmm.
You assume a constant fracture propagation rate.
Right.
Are there complications associated with that?
Yeah, so again, I think this is similar to Yunzan's question. I think the velocity will only change, it will only determine the magnitude of this signal, and it will not determine, or it will have less impact on the shape of this signal. So I don't think varying velocity will change this. Although I think it's a lot of people have this question, and Payal, that's probably your task here. Is we can actually having a fracture that propagated with a different velocity, and then we see whether this in the DDM, and then we can test whether this still stands. But from the analytical solution, I believe the velocity shouldn't matter.
Excellent. And Yvonne Gill's question is, can you speculate or do you have simulations that suggest what the effect of different rock mechanics properties might be?
Um,
Modulus.
I think that's again, I think only from the analytical solution, only the Poisson ratio will impact this. But we did test the different Poisson ratio, and we believe it's only, Payal, if you remember, can correct me, but less than a few percent change on the coefficient. But the linearity is still there.
And my friend Ali is suggesting that rectangular fractures don't occur, and that might not be a useful simulation. But
I agree. We basically using that as a upper bound, right? Worst case scenario, the most unrealistic possible cases, but even that linear relationship predict, a thing that less than 10% of error.
So Ken Do has a more practical question. That suppose you have is there an influence of the number of clusters in a stage and how close those clusters are together, and
Yep.
What's a practical limitation of the distance that you can sense? I think you've covered that.
Yeah, no, that's the practical distance. I already covered that. This is an excellent question, and because basically with the issue with the multiple fractures is that it still exists. This hardship still exists. This relation still exists. But if you have a multiple fracture propagate together, their strain field gonna linear impose on top of each other. So the strain field that from other fractures may distort your heart-shape signal. And so that may, break that linear relationship to some degree. So usually what we're observing at this point is basically we're picking the first fracture arrival, which have the cleanest, most undisturbed heart-shape signal, and use that for the prediction. This actually even that have some unique application. For example, the number if you're testing cluster distance spacing, and for the one of the thing is that if the fracture are fighting too much with each other, and the fracture are too close, that may push the first fracture to propagate much faster than a situation that you have more even fracture growth, right? So just by measuring the velocity like this and comparing it with the different completion designs, you actually can get insight about the fracture, multiple fracture propagations. But it is a limitation that if your the heart shape is actually in the middle of the stage between multiple fracture hits, you may have difficulty of picking the correct pick.
And Andres's question is are there equipment limitations or frequency limitations depending on whether you use Rayleigh or Brillouin frequency to determine these measurements? What sort of sensitivity do you need, particularly in a hard rock?
Yeah. We haven't really changed this to strain rate yet. That's an excellent question. So because you can see this hardship signal are relatively weak, lower magnitude compared to the signal we have after the fracture hit. So definitely higher sensitivity instrument are able to enable us to pick this hardship at a further distance away. Yeah, so I don't have a good answer to that. But I think, Andre, this is, this is off the sense data and we capture this very well. So I will appreciate from the hardware side that we can get even more sensitive instrument.
So Scott Butts has an interesting question. Can you apply this similar technology in inverse after the fracture has passed the monitoring well?
We have, this is actually a work we did with Yunzhan when he was at the Texas A&M. We actually analyzed the strain field after this. We find that most of the strain after the fracture hit is dominated by the fracture width at the aperture at the monitor location. And similarly, theoretically, you should be able to, but the other signal, the stress shadow and also the tensile strain of the fracture opening at the monitor well, those near field strain are dominating this. So you are not able to capture this very weak tensile signal after fracture tip pass. So we have a couple of paper published on SPE journal. Basically, we derive a geomechanical inversion algorithm to invert for fracture width after the fracture hit, and we are able to capture, let's say, 90% of the signal observed in the data. So to your answer, the answer to your question is probably not, simply because at that time your data is overwhelmed by another type of signal from the fracture.
And we're running late, but hopefully I can push 3 more questions.
Okay. Thank you everyone for asking so many questions.
And Alexei, I mean, we're gonna let him ask a second question just this one time. And he wants to know if you're planning to extend this to multiple fractures. And I think you probably talked about that.
Yeah. I think there's our difficulties associated with that. Yeah.
And Claudio is interested if you've been able to calibrate this with other measurements such as tracers.
Tracers are not able to tell you this fracture propagation speed, let's say. So this is a very dynamic measurement, right? So we already know there's a fracture hit in here. We just want to constrain a little bit further before the fracture hit. Microseismic maybe, but the relation between microseismic strain is very formation dependent. So a lot of time I feel like I trust this strain measurement more because it's, you can almost predict this with the analytical solution, simple analytical solution, then the microseismic can be more effective at many other things. So to your answer, haven't seen a measurement with a comparable confidence of this fracture propagation, compared to string data. I would like to discuss if you think there's one.
And then Mirko, we're going to let Mirko ask a second question. What about the shadow zone? Is the size or maximum amplitude trajectory also related to a distance or a fracture width?
What's the size of the maximum trajectory? So basically, if I understand it correctly, for this heart-shaped signal, the amplitude of this heart-shaped signal is determined by the fracture width. And the shape, the distance, the shape of this heart signal is determined by the fracture tip distance. So these are decoupled from each other. I hope I understand your question.
Well, you guys can follow up independently if there's more discussion on that. But
Right.
wow, this fantastic presentation, huge amount of interest, and really very nifty to be able to look at fracture velocities and
Yeah.
and everything that can be done in practical application. So on behalf of everybody, I really want to thank you from a great presentation.
Thank you very much. Thank you so much for inviting me. And thank you everyone for showing up. And yeah, and